Greetings, I'm Yvonne Stapp for Science for the Public, and I welcome you to Contemporary Science Issues and Innovations, recording today with the Belmont Media Center at the Belmont Senior Center. Our distinguished guest via Zoom is the famous astrophysicist, Dr. Mario Livio, to tell us about his most recent book, Is Earth Exceptional?, which he co-authored with Nobel Laureate and geochemist Jack Szostak. And Dr. Livio in the book addresses the prospect of life elsewhere in the cosmos, a question he himself has discussed numerous times during his 24 years at the Hubble Space Telescope. The book itself combines the conditions necessary for life and also the combination of distinct conditions and ingredients that lead to the emergence of life on Earth. So let's hear now If Earth is Exceptional. Dr. Livio, welcome and thank you very much for joining us again today.
Thank you very much, Yvonne, and it's a pleasure to be there. I understand that the climate there is not exactly cooperating, but let's hope that I'm glad that you all made it here. So, as Yvonne just mentioned, my talk is based on our new book, together with Nobel Laureate Jack Szostak, Is Earth Exceptional? The Quest for Cosmic Life. Just to introduce ourselves, this is me trying to put together a galaxy, as you can see, and this is Jack in his lab, trying to put life together in his lab. The two questions we are dealing with in this book, and which I will very briefly describe in this talk, is how did life on Earth begin, on one hand, and second, are we alone in our Milky Way galaxy, or maybe even in the universe at large? Now, amazingly, I'm sure you know that for thousands of years, humans thought that they actually know the answers to these questions. For example, how did life begin? Well, this is how Michelangelo envisaged it. God created it. And how was the Milky Way formed? In Greek mythology, it was spilled milk by Hera, who didn't want to feed the baby Heraclius. But of course, we today have different answers to these questions. We live on our Earth, which looks very beautiful from space, but from nearby. The Earth itself is part of the solar system. In the solar system, we have three planets that in principle could support life in the sense that they are rocky planets, and these are Venus, Earth, and Mars. Mercury is far too hot to have any hope for ever sustaining life. Now, the other planets, Jupiter, Saturn, Uranus, Neptune, they are large gaseous planets, so themselves they don't have a surface on which life could emerge. However, they have many moons. Jupiter has 95 named moons, and as you will see, some of those perhaps can sustain life. Saturn has 146 named moons, and again, some of those in principle perhaps could sustain life. So I'll mention all of those. Where Earth from a distance looks very different. I'm not sure if you can even see it. In the rightmost band here in the middle, there is a pale blue dot. That is Earth, how it looks from one of the spacecraft from a distance of about 4 billion miles. This is how it looks, a pale blue dot. And this is nevertheless the only place so far where we know that life is. Now, what is life? I mean, what does life consist of? Life seamlessly manages to combine four processes. One is metabolism, which means that life is able to take energy and nutrients from the surrounding and use them. There is genetics, which means life has an information system that is capable of transferring information from one generation to the next. Life as we know it is characterized by compartmentalization, which means all life we know is made of cells. And the fourth thing is catalysis, namely, there are processes that make more efficient and speed up chemical reactions. So when we are looking for life, we're looking for systems that are capable of doing these four things together. The problem is that for many years, one of the serious problems that researchers encountered was that there is a self-referential thing in life, a bit like this drawing by Escher, where one hand draws the other hand, but each one draws the other. So, for example, you probably know that DNA is important for life. But if you want to make DNA, to produce DNA, you need some enzymes, which are proteins, which you need in order to produce DNA. But to produce those enzymes, those proteins, you need DNA. So there is this circular type of dependence that everything in life as we know it today depends on everything else in this circular way. And for many years, this was thought to be an enormous obstacle to any kind of theory that would say, how did life start? We now know a little bit more, and in particular, two researchers, Thomas Cech and Sidney Altman, they actually received the Nobel Prize for this. They discovered that RNA, not DNA, but RNA actually can act like a protein enzyme. So, in some sense, RNA can be both the chicken and the egg. It can be both, the nucleic acid that we need, like RNA, and it can act like a protein enzyme. And this thing led to this idea that is called the RNA world, which means that we now think that life on Earth started, there was no DNA, there were no proteins. It started just with RNA. And RNA was acting both as the molecule that has the information and manages to transfer it from one generation to the next, and as a protein enzyme which can speed up chemical reactions. Now, I have to tell you a little bit about what RNA is made of. RNA it has a sugar phosphate backbone, which is this thing that runs along here. And all the information is in four bases, which are called for short C, G, A, and U. So there are these four bases. They contain all the information, C, G, A, and U. And you need to make these bases in order to make RNA. Because you see, once we have the idea of the RNA world, it means that the whole problem of how did life on Earth start reduces to how was RNA produced. If we can answer that fully, then we already know how life could have started. So we basically need to make sugars, we need to make phosphates, we need to make these C, G, A, and U bases. It turns out that phosphates, they were there. These were molecules that were there. So basically, it remains to make the sugars and to make these four bases. There is something very strange about the origin of life. You see, the bases in RNA, they contain mostly carbon and nitrogen. So it helps if you want to make these bases, if you start with molecules that already have carbon and nitrogen in them. And it turns out that the molecules that have that are either considered today very strong poisons like cyanide or formaldehyde, or they really stink like hydrogen sulfide, which it turns out also helps in the reaction. So, believe it or not, we think that life started with poisonous or stinking molecules. Now, how do we think the whole process may have begun? Uh, Hydrogen cyanide formed in the Earth's atmosphere, from where it rained down onto the ground. Iron leaked from the ground, from volcanic areas and so on. And they combined to make ferrocyanide. And the good news about ferrocyanide that it forms a salt which can then accumulate, and you make these reservoirs of ferrocyanide, which later you can use the cyanide to make the bases that I mentioned, C, G, A, and U. So this is the idea. Now, how do you release the cyanide from the ferrocyanide? You need some sources of heat, but those were abundant in the early Earth because there were volcanic active areas and also areas that were impacted by asteroids that came and hit the Earth. So all of those could release the cyanide and make it work. I don't want you to read all of this, and you don't need to really look at these molecules. I just want to mention one thing that researchers found along the way, that you might have thought that since RNA is made of a sugar, a base, and phosphate, that you need to take a sugar and a base and combine them and then combine with a phosphate. Well, it turns out that that doesn't work. And the researchers who work on this, in particular, John Sutherland in England, showed that what works best is that you actually form some intermediate molecule, which then gives you what you need. And in particular, the intermediate molecule that proved most helpful is known for short as RAO. And RAO has, again, like the ferrocyanide, which made the salt, RAO can crystallize and thereby, precipitate out of the solution and be available for the next thing. Let me give you the bottom line of this. Where are we in terms of researchers finding ways to create all these things? Researchers have been able to show that of the 4 nuclear bases of RNA, the nuclear bases C and U could form in the precise conditions that existed on the early Earth. So 2 out of the 4 nucleobases, we know how they could have formed exactly just by pure chemistry on the early Earth. More than that, you may know that proteins, which are the other part of life, are made of amino acids. In fact, precisely 20 amino acids. All life forms that we know are made of 20 amino acids. Well, what researchers managed to do is to show that precisely the same simple chemistry that could produce C and U on the early Earth could also produce to at least 12 of the 20 amino acids that are found in life. So, just to give you an idea where we are, we don't have life yet in the lab, but we know how on the early Earth, from the conditions we know existed, 2 out of the 4 nucleobases could have formed. and 12 out of 20 amino acids could have formed. There is one more thing that is needed for life, and that is cells. And by that I mean a membrane that surrounds, that is a wall for the cell. Basically, we think that the protocells or initial cells of life were nothing but a wall inside which there were some pieces of RNA. I told you that RNA was enough to do the trick. Now, we know how to make some such membranes. When I say we, I mean researchers know how to make some such membranes from some simple, relatively simple fatty acids. Now, they are not quite the membranes that we see in cells today, but they can do the trick in terms of that such cells can divide quite naturally and grow when fed by nutrients and so on. So we are, again, part of the way there, not quite with the more clever membranes that cells today have, but part of the way there. By the way, why do we think we need cells at all? Cells were needed for Darwinian evolution at the molecular level, which means, how does Darwinian evolution work? It's the strongest are the things that survive and continue to multiply. So what you need is a situation where if a certain RNA molecule was able to do something in a better way, you want to keep it there so that it will give it to the things inside that cell and not that everything will drift apart and not be able to benefit from that. Now, you may ask me, what is the earliest form of life found on Earth? The answer is the earliest form of life is about 3.5 to 3.7 billion years ago. And it was found in these things that are called stromatolites, which are really like mats of bacteria-like things that are found and fossilized and with that type of age. So that's when we think life started. There is another question, which is where did life start? And there I want here to try to dispel a certain myth. If any of you has read much about origin of life on Earth, you probably heard many times that life may have started at hydrothermal vents at the bottom of the ocean. Now, Jack and I don't think that that can be true. And there are many reasons that we think that. I wouldn't say that everybody agrees with us, but many important researchers do. And the reasons are, well, first of all, those who advocate hydrothermal vents as the place of origin of life have never been able to actually show how the real chemistry could have worked at hydrothermal vents. Second, and perhaps most important, is that all the experiments on origin of life have shown that you need a few key molecules and you need them at high concentration. Only that then can you get the chemical reactions needed to go to the next steps. Well, to get high concentrations at the bottom of the ocean is virtually impossible because everything is immediately diluted and lost. And the third thing is that, again, I didn't give you all the details of how those molecules come together and so on, but UV radiation, ultraviolet radiation from the young sun was very important, but UV radiation does not penetrate to the bottom of the ocean, and therefore we don't think it is there. Where is it? We think in actually ponds and relatively small lakes or impact craters where asteroids hit and generated a small lake on the surface of the Earth. That's where we think life actually did start. I'm moving now beyond Earth. Is there life anywhere in the solar system? Well, Mars has been explored the most. The Perseverance rover is still there on Mars, but Mars looks like a desert, and there is no water on the surface, but there is water deep underneath the surface. And there is evidence that there was water once on the surface about 4 billion years ago. So life could have once existed perhaps on Mars. And by that I mean very simple bacterial life, not, there were no crocodiles there. But two experiments in the past claimed to discover things that look a bit like life. And this is an experiment on the Viking landers many years ago that turned out not to represent life. And there was a meteorite, ALH 84001, that came from Mars to Earth, and it was thought to harbor some form of simple fossilized life, which again turned out not to be life. So far, we have not found life on Mars, but the search continues. About 2030, samples collected by Perseverance will be brought back to Earth and further analyzed to see if there is any past life. Venus was not thought for many years to have much life in it, in particular because it's very hot. On the surface of Venus, lead would melt. But in the past 3 years, in the upper atmosphere of Venus, there are found small traces of phosphine and ammonia, molecules which on Earth are associated with life. That doesn't mean that there is life on Venus, but again, that is going to be further explored. I told you that Jupiter itself cannot have life, but it has a few moons. Europa has a deep ice layer on top, but underneath the many miles of ice, there is liquid water. We don't think that life could have started there, but if life was somehow brought there by an asteroid, let's say coming from Mars, with life in it, perhaps life could be sustained in that underneath ocean. To study Europa further, the Europa Clipper was launched this last October, and it is going to again reach Jupiter in the 2030 timeframe, and it will study this. Saturn, again, itself does not have life. It's a gaseous planet, but it has a few interesting moons. Enceladus, which, like Europa, has a deep ice layer on top, but a liquid ocean underneath, which could perhaps sustain life. It also has the moon Titan, which not only has an ocean underneath, but also has some lakes on the surface, only that these lakes are not of water, liquid water, they are liquid methane at extremely low temperature. So if liquid methane could somehow harbor life, then it would be interesting to explore. But I must say that there isn't very much interesting chemistry happening at those temperatures, so don't hold your breath. NASA had once a program to land a boat on one of these lakes. I even suggested, this is Titan, so I suggested that the boat could be called the Titanic. But in any case, that program is not happening. Now, what about the Milky Way galaxy? Around many young stars, we see disks of gas and dust, just like the one from which we think our own solar system happened. And we now know of more than 5,800 planets orbiting stars other than the sun. Many of them are actually kind of Earth size, and even are in what is called the habitable zone, which means that distance from the star where the temperature on the surface is neither too hot nor too cold, so it can have liquid water on the surface. Now, how do we search for life on planets around other stars? By what is known as transit spectroscopy. The idea is the following. For some of those planets, the planets orbit the star in such that the orbit is in our line of sight. So when the planet comes in front of the star, some of the light from the star passes through the atmosphere of the planet. So by looking at that light and analyzing it, especially now with the James Webb Space Telescope, we can tell the composition, or at least part of the composition, of the atmosphere of that planet. This system, TRAPPIST-1, has 7 planets that are sort of similar to Earth. 3 of them are in the habitable zone. Unfortunately, so far, most of them were found not to have an atmosphere at all. Another planet that has been talked about, K218b, there was a claim that they found a certain molecule, dimethyl sulfide, which again on Earth is associated with life, but that detection is not very certain. So basically, so far, we have not found anything. Now, what about other galaxies? There are lots of other galaxies. You know, if you look at the James Webb Space Telescope deep field, we can estimate that in the observable universe, there are no fewer than about 2 trillion galaxies. So, that sounds like, yeah, there must be life somewhere. Well, it's not so simple. The experiments with life on Earth have shown that, there is lots of things need to happen for life to have started. And since we don't know the probability for life to have started, it is very difficult to say whether, even with this large number of galaxies, whether indeed we can be sure that there is life somewhere. What about intelligent life? Well, we think that intelligent civilizations will be very clever in using the energy of their star by building perhaps something like around their star and collecting that energy. But, if that is true, and if these intelligent civilizations are more advanced than us by maybe 1 billion years, then we have no idea even how to exactly look for them. And not only that, they may be machines, they may be AI machines, because it is not impossible that within not too long, AI will take over and will be the dominant species. Another search that is taking place is searching for potential artifacts from maybe some other civilization visited Earth. Again, there have been some claims of finding things. Most of us don't find those claims convincing at the moment. So the real answer is that I cannot tell you whether life on Earth was a freak accident or a chemical inevitability, because we don't know what the probabilities are. So I want to finish, before I take questions, with 2 points I want to make. One is, you see, if you look at how life and so on started in general, we had stars forming, those stars lived, and then they ejected their stuff into space, either via supernova explosions or a more gentle process called planetary nebula. All the materials that make for life, you see, in the Big Bang, only hydrogen and helium were formed, and tiny traces of other elements. All the elements that are needed for life, carbon and iron and so on, and this were formed inside stars. Not only that, you see, this atom in my body was at one time in one star, and this atom could have been at completely another star. So not only are we in the universe is inside us. We are intimately connected to the universe. That is a very important point. And lastly, I want to finish with this thing that philosopher Immanuel Kant once wrote. Two things awe me most: the starry sky above me and the moral law within me. If I translate that to our scientific language today, is we want to understand three origins questions. How did the universe start? How did life start? And how did consciousness appear? We have made enormous progress on how the universe started by, this picture of a big bang, a hot big bang. I just told you that we made a lot of progress in understanding the origin of life, even though we don't understand everything yet. I think we're probably least advanced on understanding consciousness. So again, I want to remind you of this book. I hope very much that some of you at least will read it, because there is so much more information here than what I could give you in this brief lecture. And I will take questions if there are.
Hi, you mentioned that the current thought of where life began on Earth is in small ponds or asteroid impact lakes. What leads you to believe that those are the likely places?
Yeah, so it's a good question. By the way, amusingly enough, Darwin once wrote that, maybe life started in some small pond like this, and we now think that he was probably right. The thing is that these small lakes, they allow for a series of processes that help in the processes that we think led to life. Wet, dry cycles along the banks of such small ponds, freeze-thaw cycles, which again, when you freeze, you help to concentrate materials and so on. And the fact that they are open to UV radiation, which we think was absolutely necessary. So as a result of this is what leads us to these particular locations.
Hi, another water question. Based upon the spectrum analyses that have been done on exoplanets, what percentage of the exoplanets do you think have water or water vapor in them?
Yeah, so water vapor is actually quite common. Water vapor is quite common, but water vapor alone is not considered a biosignature, because water is maybe a necessary condition, but is definitely not a sufficient condition. So the first thing we want to try to see if there is water, but then we want to find some real biosignatures. And biosignatures are things in particular that are out of chemical equilibrium. Like if you find both a high concentration of oxygen and methane in the atmosphere, that you almost cannot do it without some life processes. So these are the real thing that we're looking for.
If life started, if you think life started in fresh water, how do we explain fish and sea creatures?
What does that mean?
Well,
I'm not
we
sure.
do have a lot of life.
Fish and sea creatures are, of course, much, much more evolved than what we're looking at. We're looking at, just the most primitive forms of life.
So, of course, you're talking amoebas and things like that.
Right, right.
How far away is the nearest exoplanet that can possibly
Yeah,
life?
I don't remember the precise distance, but it is a few light years.
Clearly, in these freshwater conditions, life must have begun independently many times over, and some of which succeeded, most of which did not. Are there any attempts that you know of to see the development of these primitive coacervates, the primitive little cells existing on Earth now?
Yes, they cannot exist on Earth now The reason is that the life that exists on Earth now consumes such things immediately. And even Darwin actually recognized that. You are absolutely right that initially life must have started, and not necessarily even life. I talked about these ferrocyanide salt deposits. So yes, you can form a ferrocyanide salt deposit, but in most cases, those salt deposits were washed away or destroyed immediately. So life had to find a certain spot where, somehow wasn't impacted by more asteroids, things like that, to survive. Now, it is also interesting that you asked about these things. There is a paper that was published like a couple of weeks ago, because if you make those, you mentioned these quasarides, which are, like drops of oil, let's say, in water. Those are nice thing in terms of that they look a little bit like cells. The problem was thought to be that they exchange matter between them way too fast. And as a result, you couldn't get any evolution there. And this research that was literally just published showed that if you add distilled water to these droplets, then you can slow down the exchange between different droplets to the point that maybe you can start to get evolution there. Now, where did you have the distilled water on the early Earth? In the rain. So rain could have been really important for the first cells to form. And this is, I'm telling you, it's a paper published literally a few days ago. So I was very amused to hear your question.
Are any of these studies of other planets, other bodies, in those studies, has there been any evidence of processes that might not be what you'd call Earth life, but were still processes that could lead to the ability to replicate, which I guess that would be, one key part of what we might call life. So do we see anything anywhere else that is maybe not Earth life as we know it, but is the beginnings of processes that might be able to sustain themselves?
No, unfortunately, no. We have not seen yet anything that, well, I mentioned, the few places where there were suggestions that maybe something was found, but all of those turned out to be, definitely not conclusive. The good news is, first of all, nothing on exoplanets, but even in our own solar system. I mentioned phosphine and ammonia in the upper atmosphere of Venus. The good news is that there is a mission that is supposed to study the atmosphere of Venus and even reduce a probe that will go through the atmosphere and study its composition very accurately. And so we will know a little bit more about these things. But so far, no. I can say that we have not seen anything that leads us to say, aha, we discovered life.
Years ago, there was a paper that suggested that life could evolve rather than using phosphate as a basic energy currency, could use arsenate as a basic energy currency. And I think that was not replicable or not. Can you give me an update on that?
Yes, yes, it was. Yes, it was a very unfortunate paper. Because NASA actually made a press release on that paper, and that paper turned out to be completely wrong, but completely wrong. I mean, not only the claim was that they found in a lake they found these cells that use arsenic instead of phosphate. It turned out, first of all, that no, there was no arsenic in those cells. And not only that, the bacteria that lived there, which presumably used arsenic, actually a more careful analysis showed that they actually did everything possible to avoid the arsenic instead of the phosphate. So it was, honestly, it was an embarrassing paper. But you're right. I mean, it made a big noise, that paper.
That's it? Okay. Dr. Livio, thank you very much for your wonderful presentation to us today. And I do hope people will see the book. It is in the library system as well and in bookstores. And Dr. Livio is a wonderful writer. So
I want to make one comment about that. The first 4-5 chapters in this book, by their nature, because they deal with the origin of life, they include quite a bit of biochemistry. Now, some of you may be a little bit rusty on your biochemistry. So,
don't worry about it.
but let me say the following, something which I honestly believe. Even if you will read just the first chapter and the last, you will learn a lot about these questions.
Yeah, that's true. That's true. It's true. Yeah. Wait 1 sec.
Dr. Livio, how many light years away are you right now? In other words, where are you right now?
I'm in Hoboken, New Jersey.
Oh,
So not too far.
a big deal, right?
Not too far.
Okay, we'll close out then. And again, thank you so much for joining us today and all the best.
My pleasure. Bye.